morning, everyone. So I see people still coming. So it's 10 a.m. and we can start. So in the previous recitation class and yesterday in the lecture, we introduced what we introduced. We introduced batteries so that we can drive simple circuits, and we also introduced capacitance. Right, the idea of capacitance. So we introduced the capacitance if you have two electrodes, right? Two electrodes, right? One is positively charged, one is negatively charged, right? So take the charge of one absolute value and divide it by the potential difference between the electrodes. And that number is exactly the same if you don't change the geometry of the system, right? So that number, that ratio, that's what we call the capacitance. And then, so again, as I told you, this formula can be applied to find capacitance of any object. But since we use parallel plate capacitor all the time in this semester, right? So we apply that for a parallel plate capacitor, PP capacitor. And we got C equals epsilon naught, and A, it's the area of the plates, D is the spacing between the plates, right? And what's the major feature of this formula? Is that it depends only on the material between the plates. Epsilon naught, it tells us that there is a vacuum between the plates. A, area, D, spacing. So it's a pure, it's pretty much geometry of a capacitor, right? And the material. So it doesn't matter how much of charge in the capacitor or what's the potential difference across the capacitor. It doesn't matter. Of course, assuming that you're working in the sort of working range of this or that capacitor. Okay, so that's what we introduced in the previous classes, but we haven't solved a problem, right, about this. So let's do it now. So the problem 2654 and similar will be in your homework 53. I already wrote it. Right. So what do we have here? A parallel plate capacitor. There will be two parts. All right, and there will be transition between them. So in the first part, okay, so first of all, area is given. It's a square 2 by 2. I will write it down. Then there is it is connected to a battery, right? Also, potential difference of a battery is given. And also in part A, the spacing between the plates is given. Some D, 1 millimeter. And in part A, we will have to find potential difference and the charge in the capacitor. In part B, we will increase the spacing by a factor of 2. And we will try to answer the same questions. And in problem 53, similar situation, right, in your homework. Similar, but not exactly the same. So we have a parallel plate capacitor. So a PP capacitor. And, okay, let me write, connected to a battery. Connected to a battery. So potential difference of a battery is 9 volts. All right. Then area of a plate of a capacitor is 2, I think, centimeters. Yeah, 2 centimeters by 2 centimeters. And now let me put part A, because the next part, the next parameter, will be different for part A and part B. So now I will write under this sign. And the spacing between the plates is 1 millimeter. And I put a subscript 1 because it's for the first part, for part A. Okay, let me draw sketch the situation. So we have a capacitor, right, connected to which, okay, this way, I put this polarity. Right. So most of you are familiar with symbols in the circuitry, right? So this is the symbol of a battery. Smaller bar represents negative electrode, larger bar represents positive electrode, right? So this is plus, here minus. So as a result, this electrode of the capacitor is positively charged, and this, of course, is negatively charged. Right? Okay, let me use different color. Okay, so that's what we have. Yeah, of course. D1 spacing, D1 area A, right? And yeah, that's it. So as I said, we need to find charge in the capacitor. There must be some charge, and the potential difference. So we need to find. Let me put first potential difference, delta V1 again, because there will be second part, and of course I will use subscript 2. So use here delta V1. So that's what we need to find, and we need to find charge Q1 in the capacitor. Right. So here it's a minus Q, here plus Q. So first, potential difference. Of course, usually students tell me immediately what will be the answer, right? Of course, potential difference across the capacitor will be equal to the potential difference across a battery, so delta V, right? But when I ask to justify, okay, let me give you this, right? So because we will need this justification in order to answer some questions in part B, right? So I used in my lecture yesterday. Look, guys, this. Let's assume it's not assume it's a 9-volt batteries. So minus 4.5 volts plus 4.5 volts. So overall potential difference of a 9 volts. So this electrode of the battery is at plus 4.5 volts, and it's a piece of metal. You remember properties of a metal? Where is my ball? So if you have a piece of metal, electric potential inside of the metal is constant, right? So if you have this electrode and it's made of metal, so electric potential everywhere the same, 4.5. Then it is soldered to a piece of wire. What is wire? It's a big piece of metal for electrons, right? So it means all these points will be at the same 4.5 volts potential. Then this wire is soldered to this this electrode of the capacitor, which is again piece of metal electrodes of the capacitor. So again, this electrode must be at the same 4.5 volts electric potential. So because basically all this left side of the circuit is at the same potential, 4.5 volts, because it's just a one big piece of metal. So this is 4.5 volts, and then I can say exactly the same about this negative side. Left-hand side. Minus 4.5, minus 4.5, minus 4.5. So the potential difference across a capacitor, in this case, all the time equals to the potential difference across a battery. So we can write so immediately. So delta V1 in this case is 9 volts. So it is equal to delta V and equals to 9 volts. Okay. So that's more or less obvious, but I just wanted to give you justification. All right, so now what about Q1? Whenever you want to analyze a capacitor, and that's what we basically are trying to do, right? You need to think about 3 parameters. I mentioned that yesterday in the lecture. C, Q, delta V, like this circuit trinity, right? We're going to see the similar situation when we start talking about resistors and inductors. Every time 3 parameters. In this case, C, Q, delta V. That's what we have in this definition of capacitance. Right? So we just discussed delta V. Then we need to answer the question about Q. So in order to answer the question about Q, we need to look at capacitance. And capacitance in this case, since it's a parallel plate capacitor, can be found using this formula, and which depends only on the geometry. And we have plenty of geometry. Area basically is given, spacing is given, right? So we know that there's a vacuum between the plates, so we should be able to find capacitance. Once you know capacitance, right, you can use this formula and find Q. So now let's find capacitance since geometry is given. So, and again, I will use subscript 1 because this is the capacitance in part A. C1 epsilon naught A divided by D1. Okay, don't forget to use correct units. 2 by 2 centimeters, so but we have to convert it to meters. And the spacing also 1 millimeter, we need to convert it into meters. So epsilon naught 8 point, okay, I will write numbers, right, which I usually don't do. And now I feel like I'm running into this. Okay, anyway, I will try to squeeze 2 times 10 to the power of minus 2 meters, and I will put to the power of 2 because it's a square, right? 2 by 2, so that's why I squared it. And divided by 1 millimeter, it's a 1 times 10 to the power of minus 3 meters, right? Okay? So if you calculate it, you will get, okay, I will write underneath C1 equals to, what's the number? 3.54 times 10 to the power of minus negative 12. Units? Yeah, there is a special unit, farad, F capital just. So actually, 10 to the power of minus 12, if my memory is not failing me, it's a picofarad. Picofarad. Right, and now we can find charge using the definition of capacitance. So finally, Q1 C times delta V, right? C1, of course, in this case, C1 times delta V1. Right. I will write immediately the answer. So it will be 31.9 times 10 to the power of what? Minus 12 coulombs. So again, picocoulombs. Sooner or later you will remember all these prefixes. Micro, nano, pico, femto. Okay, so that's what we wanted, and that's what we needed. Okay, so that's part A. You know what? Probably I should have used blue too. Right. That's part A. Now part B. In part B, as I said, let's increase the spacing. Okay, let me move away from the writing. Let's increase the spacing by a factor of 2 and answer the same questions. What will be the potential difference and what is the charge? So now D2 equals 2D1, which is, of course, 2 millimeters. So we double D. So we double D. And first, again, we will basically what we need to analyze the capacitor. Analyzing capacitor means you need to know C, you need to know Q, you need to know delta V again. 3 parameters all the time. And of course, remember that C, inside of C, we have plenty of geometry. So delta V. Will it be any different? Delta V2 now, okay? Okay, let me write so what needs to be found, and then, so find delta V2 and of course Q2. Using the same arguments which I gave to you to justify this, that the potential difference across the capacitor equals to potential difference across the battery, is still applicable here. You increase the spacing, so what? If you assume that your battery is good, right, is healthy, strong enough, right, it will be able to provide whatever is needed, but the potential difference will be exactly the same, right? So I can give you exactly the same arguments, and the potential difference in the second part will be still equal to 9 volts. So in this case, when capacitor is connected to the battery, to a battery in general, potential difference across a capacitor will be equal to the potential difference across a battery. All right, so let me write. So delta V2 equals to delta V and equals to 9 volts. Like in part A, the same justifications. Right. Okay, and now, so we know delta V, again, the same 3 parameters. We need to answer the question about Q, so we need to first address C. Since we changed geometry, and I told you that capacitance depends on the geometry. Since we changed geometry, we increased the spacing, so capacitance must be different. So let's find capacitance. Right. So let me write. You know what? No, I'll save some space. First, I wanted to write, since we changed the geometry, to emphasize that capacitance depends on the geometry, right? But I want to finish this problem over here in this part of the whiteboard. All right, so like this, C1 epsilon naught A, we didn't change plates, so area is the same, divided by D2 now. And as you noticed, probably, I don't like plugging numbers. It's probably my least favorite part of solution. I like dragging symbols, right, so that you can get a general formula, you can analyze it, right? But plugging numbers, my least favorite part. So, of course, you can plug numbers because you know everything, but I don't want to do that. I want to recycle what we already calculated. Recycling is good now, right? You know. Okay, so I will just write this. Epsilon naught A and divided by 2 times D1, because D2 equals to D1. And, of course, what is this? It's a C1, which we calculated here, right? So I can write, so C1 divided by 2. Okay, this 2 looks too fancy. Right. And still, I don't want to calculate, because that's not our final destination. The destination, we want to get the charge. Okay, so now we can get charge Q2 by multiplying C2 and delta V2. Right. So then, of course, Q2 equals C times delta V. Right. So C2 times delta V2. So C2, it's a C1 over 2. So I plug it here. C1 over 2 times, and delta V2 is just a potential difference across the battery. And still, I don't want to calculate, right? So look, what is, okay, let me use different color because it overlaps with that. C1 times delta V. C1 times delta V here. Delta V1 and delta V, it's the same, right? So C1 times delta V, it's a Q1, which we calculated, right? So this is Q1. As a result, I can write it's a Q1 divided by 2. Okay, Q1 is this. Okay, I can even sort of show where is that Q1 here. So I'll plug it there, and I can get the answer. And the answer is, yeah, it's basically almost 32 divided by 2. It will be, give or take, 16. Right. So it will be approximately 16, again, picocoulombs, but let me write in terms of 10 to the power. 16 times 10 to the power of minus 12 coulombs. Right. So that's the charge in this case. Let me ask you this. So look, initial charge when the spacing was d1, 32, okay, give or take, 32 picocoulombs. Now, when we increase the spacing between the plates, now it's a 16 picocoulombs. Where did that charge go? So obviously charge in the capacitor went down. Before we had 32, now it's 16. So half of the charge ran away somewhere. Where did it go? What happens? Okay, probably I'll move to this side, right? Some students see, whenever I ask this question, again, in normal semesters, right, when we are all together in the classroom, right? Some students see, but very often students don't see immediately what happens, where does this charge go? And the answer is very simple. There are not many places to go, right? There is only there are only a battery, and a capacitor. And so they can share electrons, right? So if number of electrons increased in the capacitor, it means that they came from the battery. They run away from the battery. But if a capacitor, amount of charge of the capacitor goes down, where does it go? Back to the battery. In this case, once you increase the spacing between the plates, half of the charge just ran back to the battery, recharging the battery. So you did work by pulling the plates apart, right? So you sweated, right? You used your breakfast to increase the spacing between the plates. And because of that work that you've done, right? Half of the electrons ran back to the battery, recharging it. So that's how you can recharge the battery, right? Pulling the plates apart. Right. But if you, let's say, if you reduce the spacing between plates, let's say to 0.5 millimeter, what would happen to the charge in the capacitor? Obviously, it will increase at the expense of, it will be increased at the expense of what? The battery will provide that additional charge. So in that case, yeah, battery will be drained, right? And not drained, but some amount of charge will be taken from the battery, and that charge will come to the capacitor. But in this case, you increase the space, charge run back to the battery, right? So by moving the plates, you can reduce the amount of charge in the capacitor, increase charge, reduce charge, increase charge, and you can play. So that's in your homework there will be different situation. The battery will be disconnected. We discussed that case in our lecture in the clicker question, and you remember what stays the same. In this case, when the battery is connected to the capacitor, potential difference across the capacitor stays the same all the time. Again, provided that the battery is good enough, is strong enough, healthy. But if you connect the battery from the capacitor, and then if you start playing with the distance between the electrodes, then what stays the same? We discussed that yesterday. Charge, right? You remember that analogy with the ocean liner, right? And people being trapped in that cruise liner, right? So, but here potential difference is the same. Okay, so that's what I wanted to discuss about this problem. And now, if you don't have any, but if you do have, speak up. Now we know how we can analyze a single capacitor. CQ delta V, right? Some geometry inside of C. But what if you have more than one capacitor? 2, 300 capacitors. So how can we analyze them? So of course we will have to find all these three parameters for each of those capacitors, right? And of course now the problem, complexity of the problem increases, right? But we're going to restrict ourselves to cases when capacitors are connected either in series or in parallel. We started discussing that in our yesterday's lecture, right? We haven't finished one slide. I will do it tomorrow. All right. But now let me just write the major expressions which we need, pieces of physics and formulas, right, which we need in order to start analyzing capacitors connected either in series or in parallel. And again, it can be used only in these two situations. If capacitors are not connected in series or in parallel, not in series nor in parallel, this method cannot be used. It will be just illegal, right? So of course, this method is, application of this method is limited. Okay, so now let me write something. I will just write capacitors connected in what? First, probably I will write in I know it doesn't matter, in parallel and then in series. So I will put a new bullet, right? So capacitors are in series, right? And, let me start with parallel. I don't know why I feel like every time I start with this situation. Right. Okay, parallel. So let me draw some simple circuit. Let's say we have a cap, then we have a second cap, and then the whole thing is connected. This electrode is, okay, positive. So just two capacitors. So let's say this is C1, C2, and that is the battery which provides the potential difference of delta V. So the idea in this method, so capacitors which are connected either in series or in parallel, we try to replace with a single capacitor, which we call equivalent capacitor, right? And when you do this replacement, the rest of the circuit, in this case, it's just simple battery, but it can be, you can have a very, very complicated circuit. That circuit must work in exactly the same way. You can spend, probably you spend weeks or days, right, building the rest of the circuit, and by changing that, you don't want to destroy the work of the rest of the circuit, right? So the rest must work in exactly the same way. In this case, potential difference must be the same across the battery in the equivalent circuit. And if some charge Q is taken, in the real circuit, in the equivalent circuit, the same amount of charge must be taken. Okay, so now in equivalent circuit. So now in equivalent circuit, we have a one capacitor, C, okay, I will write later. All right, and the battery, oops. Right. So this is delta V, the same, and now this is C equivalent. And as I said, if charge Q is taken from the battery, exactly the same charge must be taken from the battery in that case. Right. And so now what we need, pieces of physics and formulas from this. So first of all, formula, how we can find C equivalent. This case we derived. We derived yesterday, right? So first, in this case, C equivalent equals, you just need to add capacitances. And if you have more than two capacitors, just keep adding. So it's a first. All right, so let me frame this. All right. And the second very important piece of physics, potential difference across an equivalent capacitor equals to the potential differences across capacitors connected in parallel. This piece, that's where students usually struggle, right? They have no troubles usually finding an equivalent capacitor, right? 95% goes through smoothly, but with using these facts about the potential differences being the same, students usually have troubles. Okay, so anyway, so delta V across an equivalent equals to the potential difference across first and across the second capacitor connected in parallel. Right. Okay, let me frame this. And the test which you have to run in order to convince yourself that these capacitors are connected in parallel, the major feature is potential difference is the same. Under any conditions, it doesn't matter which battery you connect over here, every time potential difference across capacitors is the same. That's the major feature of things connected in parallel. The same will be when we start talking about resistors later on. You can connect anything. People, motors, bulbs, whatever. If potential difference stays the same, that those things are connected in parallel. Okay, so that's what we need to know about caps in parallel. Now, caps in series. In series, okay, let me first draw. Let me first draw the situation. All right, so let's say first capacitor, second capacitor, and everything is connected or is driven by a battery. So let's call it C1, C2. This is delta V. And again, the same idea. You want to simplify it to the simplest possible circuit. So instead of these capacitors, you have only one single equivalent capacitor. So you will have something like this. And again, when you do this replacement, the rest of the circuit must work in exactly the same way. So this is C equivalent, and this is still delta V. And if some charge Q is taken from the battery in the real circuit, exactly the same charge Q must be taken from the battery in the equivalent circuit. Right. The rest of the circuit must not be disturbed. Okay, and now let's write similar pieces of physics and formulas. First, how can we find this? We need to deal with reciprocals. Usually my least favorite. I don't like dealing with reciprocals. So 1 over C equivalent equals to 1 over C1 plus 1 over C2 plus and so on. These are 1. Okay, let me write it better because some students get confused. They think it's a L. 1, 1. All right. So we will derive it yesterday in the first maybe like 5 minutes of the lecture, right? Because I didn't do it. We will derive it tomorrow. We will derive it tomorrow. So because we did not derive it yesterday. And all right. So now, what is the same between the equivalent capacitor and capacitors connected in series? Again, I will prove it tomorrow. Charge over here in the equivalent capacitor and charges in these capacitors are exactly the same. So here potential differences are the same, you see, but in case of a series, Q equivalent equals to Q1 equals to Q2 and so on if you have more than 2 capacitors connected in series. Right. Okay, so that's what we need. These formulas and these important pieces of physics, because you will see in a second how these can be used. So I have to erase this, right, in order to discuss problem. Right. And quite often, problems like these I give on the exam. I will erase everything. Yeah. So where is my problem? It's here. Yeah, 2657. So it's still chapter 26. Problem 57. We have 3 capacitors connected in this way. And of course, connected to the battery. Okay, let me bring my notes closer. So first, you know what? Let's arrange our whiteboard in this case. And you also. Leave some space above. I will start drawing my circuits, and there will be 3 of them over here. And I leave some space above so I can write above, and then some space below so I can write below. I saw it in this book, and I found it very convenient, so I like it, so I'm trying to use it. Not trying, I just use it. Right. So first, we have a battery, right? So delta V, right? And then two capacitors. The first one, then the second one. They are connected like this, and then there is the third capacitor. And like that. Let me check. Yeah. And now let me label them. Actually, let me label also this using different colors. So that is delta V. This is C1. This is C2. And this will be my C3. So now let me write numbers, because numbers are given. So delta V is 9 volts. So that's the potential difference across provided by the battery. Then C1, 4 microfarad. So you see numbers are very small for micro, because 1 farad is a gigantic capacitance. I think capacitance of the Earth is, I think, a few farad, and the Earth is gigantic. So then C2 is 12 microfarad, and C3 is 2. Right, so that's what is given. And we need to analyze it. So we need to analyze it. It's the circuit. What does it mean, analyzing circuit? It means that you need to know everything about the circuit. And in this case, okay, from the electrical point of view. And in this case, battery, potential difference is given. What else do you want? Capacitors. And you remember, each capacitor, you know everything about the capacitor if you know 3 parameters, C, Q, delta V. So C's are given. So we need to find all delta V's and all Q's. That's what we need to answer. But that's what we need to find. So we need to find delta V. And I will put like 1, 2, 3. All delta V's. And all Q's. 1, 2, 3. And charges in each of these capacitors. Right? Okay. So that's the problem. And now what can be done? These capacitors are connected in series and in parallel. So this method can be used. So first of all, we just need to simplify this circuit to the simplest possible. Why? We'll see. Right? So first, I usually ask students, so which 2 capacitors out of these 3 connected either in series or in parallel? Usually the answer is obvious, right? So C1 and C2, they are connected in parallel. Because potential difference across this capacitor equals to the potential difference across that one. It doesn't matter which battery you connect. All right, so these 2 guys are connected in parallel. Right. So as a result, we can simplify this circuit to the next one. Right. So battery works in exactly the same way. Then, instead of these 2 capacitors, we have C12. Notations is self-explanatory, right? Since we replaced capacitor C1 and C2, so that's why I labeled an equivalent capacitor as C12. Right? C3 we did not touch, so it stays there. So this is C3, and it's still connected to the same battery, right? So it's still the same delta V, right? And if charge Q is taken from this battery, exactly the same charge is taken from this battery, right? Like we discussed over there, right? And so now let's find C12. Since these guys are connected in parallel, so we just need to add C1 and C2, right? According to that formula which we derived yesterday. All right, so as a result, we can find so that C12 equals C1 plus C2. C1 is 4, C2 12, so it's a 16 microfarad. Okay, let me frame it because I will need it at some point and it will be easier for me to search. All right, so that's the value of C12. But again, it's not the simplest possible, so we have to make one more step. And these two capacitors are obviously connected in series. All right, so we can simplify that circuit and find the final equivalent circuit using that formula. Right. So now these guys are obviously connected in series. Right. And so the final circuit, again, the simplest possible. So now it will be C equivalent connected across battery. And again, battery must work in exactly the same way. Again, the same delta V and the same charge will be taken from this battery, because that's how we develop the whole method, that the rest of the circuit works in the same way. Okay, and now, we need to find the value of C equivalent. So now, C equivalent, we need to use reciprocals. So it will be 1 over C equivalent equals to 1 over C12 plus 1 over C3. C12 and C3. Bring to the common denominator. Okay, I need to speed it up, right? Bring to the common denominator and then flip it. So as a result, C equivalent will be equal to the product C3 times C12 divided by C3 plus C12. Very common mistake. Students forget to flip. They find 1 over C equivalent and treat it as C equivalent. Very, very, like 15, 20% of students, right, every semester made that silly mistake. Right, so if you plug C12 and C3 here, you can easily find, I will just use my notes, 16 over 9 microfarads. Right. So that's our final C equivalent, the value. Now, okay, we simplified. So now what can be found? Now we need to find something. Since the circuit is simple as possible, like the problem which we discussed at the very beginning of this class, right? So we should be able to find the total charge taken from the battery, right? Let me write the formula which we will need. C, definition of capacitance, Q divided by delta V. Every time when I solve the problems like this, somewhere in the corner I write this formula, because now we will have to use it a lot. Right? So we know C equivalent. We know delta V battery works in exactly the same way, so it's the same 9 volts. So we can find the amount of charge taken from the battery. And that amount of charge is the same here and the same there. So that's basically we found something about our complicated circuit. Right? And if I ask you from the very beginning, for example, tell me the amount of charge taken from the battery over here, I doubt that you will be able to tell me, because the circuit is not that simple. But in this case, finding total charge is a piece of cake. That's the beauty. So we simplified, now we can find charge, and then we'll start finding the rest. Okay, so now let me find the charge. Where I can write it. So let me write Q equals C times delta V. So it's a C equivalent times delta V. That's why I needed that formula, because now I'll have to use it in a different way. right? So it will be C equivalent 16 over 9, and delta V is 9 volts times 9 volts, and so it will be 16 microcoulombs. So that's the total amount of charge taken from the battery. And so now basically now we just created like a crack in the wall. Once you create the crack, yeah, you can expand it to see the whole truth and nothing but the truth, right? So now, once we made this crack, now we can start moving back, revealing the whole truth. So let's start moving back. And now we will have to use these blue bridges, these blue pieces of information. Look, how can we go back to this? This equivalent capacitor replaced which capacitors? This one and that one, connected in series. What do we know about those capacitors, 3 capacitors in series? So this is the case. Charges are the same. Charge in the equivalent capacitor, which we just found, equals to the charge in the capacitor this and the capacitor that. So we're using this now. Okay, so yeah, these are in series, so I will just write that Q equals Q12 equals to Q3 and equals to 16 microcoulombs. So basically, that's the, I call that like a bridge which we use in order to move from this circuit back to that one. And now, look, now we know the charge in the capacitor C3. If you know charge in the capacitor and you know the value of the capacitor, 2 microfarads, can you find the charge? Piece of cake. Again, the formula, you know charge, you know capacitance, you know charge, you can find potential difference. Again, you see every time we use that formula. Okay, so now underneath I can write, so delta V3, so it will be Q divided by C. Right, so delta V3, it will be equal, Q3 divided by C3. Yeah, and so this Q3 comes from the bridge, 16 microcoulombs. So it will be 16 microcoulombs divided by C3, 2 microfarads. So it will be 8 volts. So now look, capacitor C3, we know its capacitance. We found charge 16, and now we found the potential difference. Work is done about capacitor C3. So we know everything about C3, delta V3, Q3, and C sub 3. So done with that. But we still have inside of, and now let's find the potential difference across C12. You can tell me immediately because the total voltage drop is 9 volts. But voltage drop across this is 8, so then there should be 1 volt across this. But let me use still the same formulas to find potential difference across the capacitor 1, 2. So it will be Q12 divided by C12. Q12 comes from the bridge. C12 here we found, that's why I framed it, because I knew that I will need it. And of course it will be, so what? 16 microcoulombs divided by 16 microfarads, 1 volt. Okay, let me hold you guys, for a couple of minutes, right? Because a little bit left. So now we know potential difference across this capacitor C12, but inside of this C12 we have 2 capacitors connected in parallel. So now we can use the next bridge. Inside of this, we have 2 capacitors connected in parallel, so we can use this. So potential difference across the capacitor of C12 equals to the potential difference across capacitor 1 and 2. So here we use charges, now we use potential differences, right? So delta V12 equals to delta V1 equals to delta V2 equals to delta V12, it's 1 volt. let me separate this, right? And let me show you that this delta V1, 2, okay, let me show it this way. It comes over here, right? Right. So this. So everything is connected, linked nicely, elegantly. Okay, and now if you know potential difference across capacitor C1, this delta V1, 1 volt, can you find charge? Piece of cake. C1, you know, delta V1, you know, you can find Q1, again, using this formula. That's why usually I write it somewhere in the corner all the time. So let me do that. So Q1 equals, Q, it will be C times delta V. C1 times delta V1. So C1 is 4 microfarad times 1 volt. So it's 4 microcoulombs. Now we know everything about capacitor C1. We know the potential difference 1 volt, and we know the amount of charge. Capacitance was given from the very beginning. And the last, exactly the same step, to find the charge in the capacitor Q2, and that will be the end. Q2 equals C2 times delta V2. Again, delta V1 again came from here. Delta V2 also comes from the bridge. Right. So C2 is 12 microfarads, and delta V2 is 1 volt from the bridge. Right. So it will be 12 microcoulombs. Done. So again, first you simplify the circuit using these formulas, how to find C equivalent. Once you found C equivalent, you can find the charge, like opening small crack. And then you start moving back using these pieces of physics, right? This and that, and you're just expanding that crack, finding the whole, all those parameters which we needed to find. Right. Okay, so as I said, I usually give a problem like this quite often on the exam. Similar idea will be used to analyze resistors connected in series and in parallel. Right? Very, very similar. And I like to arrange it in this way. Sort of nicely, everything is nicely linked, connected, right? And it's one of those things which I like in this book. Right, guys. That's what I was planning to discuss. Sorry for holding you a little bit longer, but I thought I would be able to squeeze in 15 minutes. Somewhere I slow it down. Okay, see you tomorrow. And if you have questions, you can still ask me.